Math 2415, Chapter 10, Vectors in the Geometry of Space, Section 2, Vectors, Video 4, Magnitude of a Vector. Now, we've already talked about the magnitude of a vector, generally speaking. We had an arrow, its magnitude was how long it is. But algebraically, we need something a little bit more, specific that actually calculates the length of that vector. So let's see if we can attack it generically and come up with an approach. Let's take a generic vector, call it A, and in component form, have its two components be A1 and A2. This is actually pretty standard notation. Whenever you have a generic vector, you can label its components using the same letter without the vector arrow, and then just subscript the components according to the position that they're in. First component, second component, if we're in R2. First component, second component, third component if we're in R3, and it could go even longer if we wanted more dimensions. So how do we calculate the magnitude of a vector? Well, visually it's an arrow and the magnitude corresponds to its length, and we can find the length using the distance formula, provided we have the coordinates of the initial and terminal point. So let's see if we can sketch this with a specific initial and terminal point, then apply the distance formula. If we're given a vector without a specific initial or terminal point, we can pick any initial point we want and then displace in the x direction and y direction by these amounts. So what's the most convenient initial point when we can choose one? The origin. If we take the origin at 0, 0, and then locate the ordered pair A1, A2, then vector A would be the vector whose initial point is the origin and the terminal point is A1, A2. Then we can simply apply the distance formula. Oh, by the way, the symbol for the magnitude of a vector, I've seen it written a couple of different ways. I'm trying to remember which one this author uses. This author uses the single absolute value bars. The magnitude of A looks like absolute value, and that's not a coincidence. Excuse me. Because absolute value technically means distance from 0. Sorry, folks. I ate a cookie between videos and part of it went down the wrong pipe. But I digress. To represent the magnitude of a vector, we're simply going to put absolute value bars around it. Heads up for those who take future math classes. In some professors' opinions, it's not really an opinion, but some professors and some authors' preferences are to write magnitude using a double absolute value bar, but it almost always means the same thing. I say almost always because even that symbol has a different meaning elsewhere. But for our purposes, we're going to represent the magnitude of a vector by simply putting an absolute value around it. In this case, it's the distance between these 2 points. Recall that the distance formula is the square root of the sum of the squares of the differences of the corresponding coordinates. In this case, A1 minus 0 in the x-coordinate, A2 minus 0 in the y-coordinate. Minus 0 doesn't change anything, so we can just ignore the minus zeros and say the square root of A1 squared plus A2 squared. We can't cancel the squares with the square roots because you cannot distribute square roots across addition. So that's as far as it will go, and that's our formula for the magnitude of a vector in 2 dimensions. In words, the magnitude of the vector is the square root of the sum of the squares of its components. I'm going to say that again. The magnitude is the square root of the sum of the squares of the components. If we were in 3 dimensions, it would be exactly the same thing. We would just need a 3-dimensional distance formula. Oh wait, we have one. So to calculate the magnitude of A, it would run the exact same course. We would initiate a vector at the origin, connect it to the ordered triple, A1, A2, A3, set up the distance formula, have the exact same thing. We would just have a third squared difference here with A3 minus 0, which means our formula would just pick up a plus A3 squared. In fact, we could generalize this. In Rn, if vector A has the components A1, A2, all the way through An, This is getting more into linear algebra, but chances are you're going to have to take that class at some point in the future. Then the magnitude of A, we could just write this formula, put dot, dot, dot plus an squared, or we could write this. It's the square root of the sum of AI squared. I begins at 1 and goes all the way to n. Now, if that last part threw you off, don't worry. It's not something you really need in this class, but it just does go to show you that we can generalize this to as many dimensions as we want. All right, I'm not going to do an example of calculating the magnitude of a vector because you're in Calculus 3. You should be able to square numbers, add them, and take their square root, or at least simplify them.